Hey everyone, welcome. Today we're tackling a really interesting string problem. The name sounds a bit complicated, but don't worry, we're going to break it down into simple, easy to understand pieces. Let's get started. Okay, so here's the deal. We're given a string that has lowercase English letters and stars. Our job is to process all the stars. Whenever we see a star, we have to do two things. Delete the star itself, and also delete one character to its left. Now, which character do we delete? The rule says we must delete the smallest non-star character that's currently to the left. For instance, if A is available, we must delete an A. If there's no A but there's a B, we delete a B, and so on. The final goal is to make the resulting string the smallest one possible in dictionary order. Let's walk through the example A star. We see the A, then another A, then B, then a third A. Finally, we hit the star. Now we have to act. The smallest character we've seen is A. We have three of them to choose from. Which one should we delete to get the best result? Well, let's think about it. If we delete the A from the very beginning, the remaining letters form A, B. But if we delete the A that's right next to the star, the remaining letters form A, B. If you look these up in a dictionary, A, B comes before A, B. So A, B is a better, smaller result. This gives us a massive clue about our strategy. The key insight here is all about prefixes. To make a string as small as possible, you want its beginning to be small. An A at the start is way better than a B. So when a star forces our hand and makes us delete, say, an A, we should be smart about which A we pick. Removing an A from way at the end of the part we've seen, well, that doesn't mess up our precious starting characters. So, the best greedy choice is this. Find the smallest character type you have to remove, and then delete the one you saw most recently, its rightmost instance. So how can we build this? A really clean way is to use a dedicated bucket for each character type. Imagine 26 stacks lined up, one for A, one for B, and so on. As we read the string from left to right, if we see a letter, we just push its position, or index, onto the correct stack. See a C at index 5? Push 5 onto the C stack. Then the magic happens when we see a star. We just scan our stacks, starting from A. The first one that's not empty holds the smallest character type we need to remove. And because it's a stack, the index on top is the one we added last, the rightmost one. We just pop it off. Simple as that. Alright, here's the full Python code that puts our strategy into action. I know it looks like a chunk of code, but we'll go through it bit by bit. It's really just doing exactly what we planned. First up, we get our tools ready. We create our list of lists, called char indices, which will act as our 26 stacks. Then, we create something called a set, which we'll name removed indices. A set is just a super fast way to keep track of things without any duplicates. We'll use it to remember the positions of all the characters we need to delete. Now we loop through the input string, character by character. If the character is a letter, we figure out its place in the alphabet. A is 0, B is 1, etc. And we add its current position to the right stack. If the character is a star, first we add the star's own position to our set of removed indices. Then, we look for the character to delete. We loop from A to Z by checking our stacks from index 0 to 25. The first stack we find that's not empty is our target. We pop its top position, and add that position to our removed set. Then we stop looking, since one star only removes one character. Finally, after we've gone through the whole string and figured out exactly which positions to delete, we build our answer. We create an empty list for our result. We loop through the original string one last time, from beginning to end. For each position we ask a simple question. Is this position in our set of removed indices? If the answer is no, it's a character we want to keep, so we add it to our result list. Once we're done, we join all the characters in our result list together into the final string. So how efficient is this approach? It's pretty good. For time, we walk through the string a couple of times. The first loop, where we handle stars, might seem slow because of the inner loop, but that inner loop runs at most 26 times, which is a constant. So the whole process is proportional to the length of the string, which we call linear time, or big O of n. For space, in the worst case, the string could be all letters and no stars. We'd have to store an index for every single character. That means the space we use is also proportional to the string's length. So, big O of n for space as well. So let's wrap it all up. This problem looked tricky, but it came down to a clever, greedy insight. To make the final string as small as possible, we had to protect the characters at the beginning. That meant whenever a star forced a deletion, we always chose the instance of the smallest character that was furthest to the right. And the perfect tool for the job was a collection of stacks, one for each letter, which let us easily find and remove the most recently seen character of any type. I hope that breakdown made sense and helped you understand the solution. If it did, feel free to hit the like button, subscribe for more videos, or drop a comment if you have any questions. And hey, if you're feeling extra generous, there's always the Boba Fund. Thanks for watching, keep coding, and I'll see you in the next one.